To accurately calculate voltage drop in an electrical circuit, you must apply the correct formula and understand the factors involved. The standard formula is voltage drop equals resistance of the wire multiplied by the current, then divided by 1000. Key to this calculation is determining the resistance of the wire, which depends on three main things: firstly, its length; secondly, its cross-sectional area; and thirdly, the material it's made from. For aluminum wire, a common conductor material, the resistance is approximately 0.126 ohms per foot. Let's consider a specific example. Suppose you are installing a 200 amp underground service using 4/0 aluminum URD cable with a wire length of 250 feet. To calculate the voltage drop, begin by identifying the known values. The length of the wire is 250 feet. The current is 200 amps. The resistance per foot for aluminum is 0.126 ohms. First, calculate the total resistance of the wire. This is done by multiplying the length of the wire by the resistance per foot. So, 250 feet times 0.126 ohms per foot, which equals 0.315 ohms. Next, apply the voltage drop formula. Voltage drop equals 0.315 ohms times 200 amps, divided by 1000. This results in a voltage drop of 0.63 volts. This calculated voltage drop of 0.63 volts is relatively small over a 250 foot length of wire. In many cases, such a small voltage drop is unlikely to cause any significant problems. However, it is crucial to recognize that the voltage drop is directly proportional to the current. Therefore, if you intend to run a high current through the wire, the voltage drop will increase accordingly. In situations where a high current is anticipated, you might need to consider using a larger wire size. Using a larger wire reduces the resistance and, consequently, the voltage drop. It's essential to always adhere to the National Electrical Code, or NEC, guidelines for wire sizing and voltage drop limitations to ensure safety and optimal performance. Always consider potential future load increases when selecting wire sizes. Remember that voltage drop calculations are essential for designing safe and efficient electrical systems. By using the correct formula and considering all relevant factors, you can minimize voltage drop and ensure the reliable operation of your electrical equipment. For example, let's explore another scenario. Suppose you are installing a 100 amp sub-panel in a detached garage, located 150 feet from the main panel. You plan to use number 2 aluminum wire for this installation. Firstly, determine the resistance of the aluminum wire. Number 2 aluminum wire has an approximate resistance of 0.8 ohms per foot. Secondly, calculate the total resistance of the wire run. This is done by multiplying the length of the wire, which is 150 feet, by the resistance per foot, which is 0.8 ohms. 150 feet times 0.8 ohms equals 0.12 ohms. Thirdly, apply the voltage drop formula. Voltage drop equals the resistance, 0.12 ohms, multiplied by the current, 100 amps. So, 0.12 ohms times 100 amps equals 12 volts. Fourthly, calculate the percentage voltage drop. This is done by dividing the voltage drop, 12 volts, by the source voltage, say 120 volts, and then multiplying by 100%. 12 volts divided by 120 volts times 100% equals 10% voltage drop. In this scenario, the voltage drop is 10%, which is often considered excessive. The NEC typically recommends limiting voltage drop to 3% for branch circuits and 5% for feeders. To reduce the voltage drop, you would need to increase the wire size. Let's recalculate using number 1/0 aluminum wire, which has an approximate resistance of 0.3 ohms per foot. Firstly, calculate the total resistance of the wire run. 150 feet times 0.3 ohms equals 0.45 ohms. Secondly, apply the voltage drop formula. Voltage drop equals 0.45 ohms times 100 amps equals 4.5 volts. Thirdly, calculate the percentage voltage drop. Or, 5 volts divided by 120 volts times 100% equals 3.75% voltage drop. Using number 1/0 aluminum wire reduces the voltage drop to 3.75%, which is within the acceptable range for a feeder. Remember, always consult the NEC tables for accurate wire resistance values and voltage drop recommendations. These tables provide guidance on selecting the appropriate wire size for different applications. Consider the ambient temperature and conductive directing factors as specified in the NEC when determining the ampacity of the wire. Ambient temperature affects the wire's ability to dissipate heat, and directing factors adjust the ampacity to account for higher temperatures or multiple conductors in a raceway. Proper grounding is also essential for electrical safety. Ensure that the grounding system is properly installed and connected to the main panel and sub-panel. Use appropriate grounding conductors and follow NEC guidelines for grounding electrode systems. Regularly inspect your electrical system to identify any potential problems, such as loose connections, damaged insulation, or signs of overheating. Address any issues promptly to prevent electrical hazards. For example, consider a situation where you need to run a 240-volt circuit to a welding machine in a workshop, a distance of 75 feet. The welding machine requires a 50-amp circuit. You plan to use copper wire for this installation. Firstly, determine the resistance of the copper wire. Number 6 copper wire has an approximate resistance of 0.491 ohms per foot. Secondly, calculate the total resistance of the wire run. 75 feet times 0.491 ohms equals 0.36825 ohms. Remember that voltage drop calculations must account for the total length of the circuit, including the return path. So, for a 75-foot run, the total wire length is 150 feet. Therefore, the total resistance is actually 150 feet times 0.491 ohms equals 0.7365 ohms. Thirdly, apply the voltage drop formula. Voltage drop equals 0.7365 ohms times 50 amps equals 3.6825 volts. Fourthly, calculate the percentage voltage drop. 3. 6,825 volts divided by 240 volts times 100% equals 1.53% voltage drop. In this case, the voltage drop is 1.53%, which is well within the acceptable range for both branch circuits and feeders. Now let's consider a scenario with a longer run and a higher current. Suppose you need to run a 480-volt, 3-phase circuit to a piece of industrial equipment located 300 feet from the main panel. The equipment requires a 100-amp circuit. You plan to use copper wire for this installation. In a 3-phase system, the voltage drop formula is slightly different. The formula is voltage drop equals the square root of 3 multiplied by the current multiplied by the resistance, all divided by 1000. The square root of 3 is approximately 1.732. Firstly, determine the resistance of the copper wire. Number 2 copper wire has an approximate resistance of 0.156 ohms per foot. Secondly, calculate the total resistance of the wire run. 300 feet times 0.156 ohms equals 0.468 ohms. Again, remember to account for the total wire length, including the return path. So, for a 300-foot run, the total wire length is 600 feet. Therefore, the total resistance is 600 feet times 0.156 ohms equals 0.936 ohms. Thirdly, apply the voltage drop formula. Voltage drop equals 732 times 100 amps times 0.936 ohms divided by 1000. This results in a voltage drop of 16.22 volts. Fourthly, calculate the percentage voltage drop. 16. 22 volts divided by 480 volts times 100% equals 3.38% voltage drop. In this scenario, the voltage drop is 3.38%, which is slightly above the recommended 3% for branch circuits. To reduce the voltage drop, you would need to increase the wire size. Let's recalculate using number 1/0 copper wire, which has an approximate resistance of 0.778 ohms per foot. Firstly, calculate the total resistance of the wire run. 600 feet times 0.778 ohms equals 0.4668 ohms. Secondly, apply the voltage drop formula. Voltage drop equals 1,732 times 100 amps times 0.4668 ohms divided by 1000. This results in a voltage drop of 8.7 volts. Thirdly, calculate the percentage voltage drop. 7 volts divided by 480 volts times 100% equals 1.68% voltage drop. Using number 1/0 copper wire reduces the voltage drop to 1.68%, which is well within the acceptable range. In addition to wire size, consider other factors that can affect voltage drop. Conduit fill. The percentage of space occupied by wires in a conduit can affect the wire's ability to dissipate heat and may require directing the wire's ampacity. Voltage drop is also influenced by the power factor of the load. Loads with low power factors, such as motors, draw more current and can increase voltage drop. Consider using power factor correction capacitors to improve the power factor and reduce voltage drop. Remember to consult with a qualified electrician or electrical engineer for complex electrical installations. They can help you select the appropriate wire sizes and ensure that your electrical system meets all applicable codes and standards. Regularly inspect your electrical system for any signs of damage or deterioration. Replace any damaged wires or components promptly to prevent electrical hazards. Use proper wiring techniques, such as making secure connections and avoiding sharp bends in the wires. Improper wiring can lead to increased resistance and voltage drop. Follow the manufacturer's instructions for all electrical equipment and components. Use the correct voltage and amperage ratings for all devices. Consider the long-term needs of your electrical system. Plan for future load increases and select wire sizes accordingly. By carefully considering all of these factors, you can minimize voltage drop and ensure the safe and reliable operation of your electrical system. This will help prevent flickering lights, overheating equipment, and other problems caused by excessive voltage drop. Ensure to use online voltage drop calculators, which are readily available and can simplify the calculation process. These calculators typically require you to input the wire size, length, current, voltage, and power factor. They then calculate the voltage drop and percentage voltage drop for you. Some calculators also provide recommendations for wire size based on the calculated voltage drop. Use these calculators as a tool to verify your calculations and ensure that you are selecting the appropriate wire size for your application. Always double-check your calculations and consult with a qualified electrician if you have any doubts. Regular maintenance and inspection of your electrical system are essential for ensuring its safety and reliability. Schedule regular inspections to identify any potential problems such as loose connections, damaged insulation, or signs of overheating. Address any issues promptly to prevent electrical hazards. Consider using surge protection devices to protect your electrical equipment from voltage spikes and surges. These devices can help prevent damage to sensitive electronic equipment. Use appropriate grounding techniques to ensure that your electrical system is properly grounded. A properly grounded system provides a path for fault current to flow back to the source, helping to prevent electrical shock hazards. Follow all applicable electrical codes and standards when installing and maintaining your electrical system. These codes and standards are designed to ensure the safety of people and property. Remember that electricity can be dangerous. Always exercise caution when working with electrical equipment. If you are not comfortable working with electricity, hire a qualified electrician to do the work for you. Staying informed and taking appropriate precautions can help you prevent electrical hazards and ensure the safe and reliable operation of your electrical system. Continuously educate yourself on electrical safety practices and new technologies to enhance your understanding and skills.